Hello everyone, today I'd like to present our work, OMG-Avatar. Let me start with the motivation. Single-image 3D head avatar reconstruction is useful in many applications. However, many previous methods are too slow or too computationally expensive for retail applications, especially diffusion-based methods and NeRF-based methods. Second, most prior work does not support dynamic level of detail, which means they cannot easily adapt to different devices. Third, the reconstructed avatar is often incomplete, especially in regions such as the shoulders. So the goal of this paper is quite straightforward. We want a method that takes only one image, reconstructs the avatar very quickly, supports multiple levels of detail, and also produces a more complete avatar, including the shoulder region. The overall pipeline contains two parts, a reconstruction pipeline and a reenactment pipeline. We start with a source image. From this image, the model extracts two kinds of features using DynAv2, the local image features, and the identity-related features. At the same time, a 3D modeler based on FLAME provides an initial 3D head mesh. Then the model builds features for this mesh in two complementary ways. The first is global feature extraction. Here, the FLAME positional embeddings are used as queries. And a transformer with cross-attention extracts global semantic information from the image. These global features are helpful for capturing the overall identity and also for reasoning about regions that are not directly visible. The second is local feature sampling. The mesh vertices are projected back onto the image plane, and the model samples local features from the corresponding image positions. These local features are important for preserving fine-grained details. But there is one problem here. Local features are only reliable for visible vertices. If a point is occluded, the sampled image feature may be incorrect or ambiguous. To address this, we introduces occlusion-aware feature fusion. It uses a depth buffer to determine which vertices are visible. For visible points, the model fuses local features with global features. For occluded points, it relies more on the global representation. Since FLAME mainly models the face and head, it does not represent the shoulders well, so we predicts the head and shoulder separately and then combines them into one unified Gaussian representation. This gives a more complete final avatar. Finally, the model predicts Gaussian attributes and renders the avatar using Gaussian splatting, and then applies a neural refiner to produce the final output image. For reenactment, given a driving image, the model estimates the target expression and pose, and then updates only the positional component of the reconstructed Gaussian avatar. This makes retail animation possible. One of the most interesting parts of this work is the course-to-fine learning strategy with multi-LOD support. Instead of directly operating on a very dense mesh from the start, the method begins with the base FLAME mesh, which has around 5,000 vertices. Then, during training, it progressively refines the representation through mesh subdivision. As a result, the model supports 3 levels of details. The key advantage is that a single trained model supports all these LOD levels. So at inference time, we can choose the level of detail based on the available hardware and the latency requirement. Now let's move to the results. On both VFHQ and HDTF, OMG-Avatar achieves the best or near best performance across multiple evaluation metrics. What is especially impressive is that even the lower resolution version, for example sub 1, can already outperform strong baselines like LOM and GAG-Avatar while using far fewer Gaussian points. Finally, here we can see the qualitative comparisons. Compared with previous methods, OMG-Avatar produces results that are more stable, more complete, and visually more convincing. Here we can see more video demonstrations. Thank you for watching.